Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Honestly, I am so excited for this one today.
Oh, me too. I mean, I want you to imagine a mechanical arm grabbing a red-hot piece of steel, weaving it through a stamping press, and then just, dropping it onto a cooling conveyor belt.
Right, with like absolute millimeter precision.
Exactly. Millimeter precision, maybe 100 times a minute. Now, imagine doing that with absolutely no computer chips.
None. Zero.
No digital code, no sensors at all. Just three pieces of solid steel pinned together and driven by a single, dumb, continuously spinning motor.
It's wild to even think about.
It is, and that is the magic of what we are digging into today. We're exploring the physical code of motion.
It really is a lost art,
Yeah.
and it's still completely foundational to our modern world.
Absolutely.
We live in an era where we just assume everything smart has a circuit board in it, right?
Yeah, if it moves precisely, it must be software.
Exactly.
Yeah.
But if you walk onto a high-speed factory floor, or if you, look inside the transmission of your car, or even open up the complex weaving loom, you aren't looking at software.
You're looking at metal.
You are looking at geometries.
Yeah.
You're looking at purely mechanical principles, taking a very simple input, like a motor, spinning in a circle, and forcing it to output this incredibly complex, highly choreographed, non-linear dance.
Okay, let's unpack this because our mission for this deep dive is to really explore two of the most fundamental mechanisms that make all of this physical choreography possible.
Right, the real building blocks.
Yeah. We are going through a stack of kinematic source material today to look closely at first the 4-bar linkage and then the cam and follower system.
Which are both just fascinating.
They really are. The goal here is to figure out how varying a few honestly incredibly simple geometric parameters can generate paths that look like they required a supercomputer to calculate.
And the beautiful truth is that they didn't require a supercomputer at all. No, I mean, they just required a brilliant understanding of physical constraints. Because when you pin two pieces of rigid material together, you aren't just connecting them,
Yeah.
You are limiting their degrees of freedom.
Right. You're telling them where they can't go.
Exactly. Understanding how to weaponize those limits is really the essence of mechanical design.
So let's start right there with the 4-bar linkage. And we're using this incredibly detailed visual atlas of coupler curves we have in our source material today.
That's a great reference.
For anyone who hasn't stared at a kinematics textbook recently, let's establish the physical reality of this setup. We are talking about 4 rigid bars.
Right, 4 bars.
They are pinned at their ends to form a closed loop. But, and this is the crucial part, one of those bars is bolted completely down to the cable.
Right, it doesn't move.
Yeah, it is the fixed ground link. It is entirely stationary.
And because that ground link is fixed, you effectively have 2 pivot points anchored in space.
Right.
So let's visualize this for you listening. Think of the base of an old, heavy desk lamp.
Okay, got it.
That base is your ground link. Connected to one of those anchored pivot points on the base, you have your input bar, which we call link A, or the crank.
A crank.
Right. Because it is usually attached to a motor, link A just spins round and round in a perfect continuous circle.
I mean, it's the easiest motion to generate. Just turn on a dumb motor and it spins.
Exactly. Just raw circular power. Now, over on the other anchored pivot point on your desk lamp base, you have link C.
The rocker.
Yep, the rocker. Unlike the crank, this one usually doesn't have the clearance or the geometric freedom to spin in a full circle.
So what does it do?
It's constrained to just swing back and forth, like a pendulum.
Okay, so we have a spinning crank on the left and a swinging pendulum on the right.
Yeah, and spanning the gap between them, connecting the free-floating end of the spinning crank, the free-floating end of the swinging rocker, is link B.
The coupler.
Ah, the coupler. This bar is entirely untethered from the ground. It is just sort of hanging out there in the air.
It's just floating between the two.
Yeah, but it's being violently pushed and pulled by the crank on one side and physically constrained by the arc of the rocker on the other.
And this is where the magic happens, isn't it? As the crank link A rotates in its boring little circle, a specific point on that floating coupler, link B, traces a path in empty space.
A very specific path.
Right. And that path is emphatically not a circle. Depending on the lengths of these bars, it traces these wild, sweeping, complex curves.
What's fascinating here is the whole concept of a coupler curve. You are tracking the X and Y coordinates of just one single point on that middle bar as the whole system just violently thrashes around.
Okay, wait, let me push back on this a second.
Sure,
Because this is where my brain starts to hurt when I'm looking at the diagrams in the source material.
it can be a lot.
If the links are just straight, rigid bars made of steel, right, and the input is a perfect circle, how on earth do they draw such fluid, swirling, irregular shapes?
I know, it seems counterintuitive.
Yeah. I mean, a straight line plus a circle should logically just yield some sort of stretched circle, right?
It is a totally fair assumption, but it ignores the physics of competing constraints.
Competing constraints.
Yeah, let's look at the tug-of-war happening here. The crank is moving in a relentless circle. It never stops, and its endpoint is constantly changing both its horizontal and vertical velocity.
Right.
That force is transmitted directly into the coupler.
So the coupler wants to move in a circle, too.
It wants to, yes, but the other end of the coupler is basically held hostage by the rocker,
Ah.
and the rocker can only swing in a fixed, rigid arc from its own ground pivot.
So the coupler is trapped.
Completely trapped. It is being dragged through these overlapping trajectories because it has to satisfy the mathematical demands of both the spinning crank and the swinging rocker simultaneously.
Wow.
And it has to do all that without either of those bars stretching or breaking.
That is, I mean, it's like tying a dog to a rotating ceiling fan and then tying the dog's tail to a swinging door.
Oh my God.
The path the dog takes is going to be incredibly complex.
That is a very vivid, if slightly horrifying, analogy.
Well, I know.
But yes, mechanically, that is exactly what is happening. The physical tension and compression forces acting on that coupler force it into paths that are highly nonlinear.
It's all about the push and pull.
Exactly. The path changes drastically based entirely on the relative lengths of those three moving bars. If you change the length of the crank by even half an inch, you completely alter the mechanical advantage.
Half an inch changes everything.
Everything. The timing of the system, the traced curve, it all transforms entirely.
And this brings up the fundamental question, right?
Yeah.
Why do we care?
Right.
Why did engineers spend decades caring so deeply about the exact non-circular shape traced by this middle bar?
Because that is how you do physical work in the real world.
Okay, give me an example. Well, real-world tasks rarely happen in perfect circles. If you were designing an automated assembly line, you might need a mechanical finger to dip down into a bin, grab a ball bearing, lift it vertically, swing it horizontally over to a housing, and press it straight down.
And you can't achieve that with just a wheel.
No, you absolutely can't. You need a highly specific, custom-tailored path in space. A linkage translates a simple rotary input, like a cheap, reliable electric motor, into that exact custom path.
That makes total sense.
Think about a standard windshield wiper. It doesn't spin, right? It sweeps, pauses infinitesimally at the edge to change momentum, and then sweeps back.
Oh, yeah.
Or think of the walking mechanisms on heavy-duty construction robotics. They need a path that lifts a foot, moves it forward smoothly, drops it down, and then drags it backward in a perfectly flat line to propel the machine forward.
Which perfectly sets up this incredible resource we are analyzing today, the Coupler Curve Atlas.
Yes, the Atlas.
For our listeners, imagine a massive multi-volume encyclopedia. But instead of words, it is just pages and pages of dashed lines forming strange shapes.
It's literally a dictionary of movement.
And historically, this atlas was a monumental achievement.
Oh,
Huge.
Long before you could boot up a CAD program and just simulate kinematics on a screen, engineers used a purely geometric brute force approach.
They did it by hand.
Or very simple mechanical plotters.
Yeah.
They took the math, varied the parameter lengths of the bars step by step, millimeter by millimeter, and plotted the resulting paths.
So an engineer in the 1960s who needed a machine part to move in a specific teardrop shape to, say, stitch a piece of leather, they wouldn't have to invent the math from scratch.
Not at all.
They would just flip through this massive atlas, find the teardrop that matched their spatial constraints, and the book would literally just tell them, you need a crank of length 1.5, a coupler of length 2, and a rocker of length 2.
It is the ultimate lookup table for physical motion. You are literally shopping for a trajectory.
Let's actually walk through that catalog. The source material outlines how these shapes evolve as we change the parameters. We can look at this as a spectrum of motion, starting with what the atlas calls the link A equals 1.5 series.
Okay, so in this series, the crank link A is the shortest bar in the system. We're fixing it at a length of 1.5 units.
Okay, 1.5.
And let's say we set the coupler, link B, to 2.0, and the rocker, link C, also to 2.0. The path traced by the coupler point here is incredibly constrained.
Yeah, looking at the atlas, it forms these tight intersecting loops. It looks like a squished figure eight or like two overlapping teardrops. It feels claustrophobic just looking at it.
And physically, it is claustrophobic. The crank is short, meaning it doesn't have a lot of leverage to throw the coupler around.
So the motor is working hard but not moving things very far.
Right. The coupler and rocker are slightly longer, so they act like stiff arms resisting the motion.
Mm-hmm.
The result is that the trace point doesn't travel very far at all.
It's just bound up in one spot.
The mechanism is tightly bound, constantly folding back over itself in a localized area.
But wait, if I keep that crank short at 1.5, but I stretch the coupler and the rocker way out, say, I make B and C 3.5 units long, the geometry in the atlas completely opens up.
Oh yeah, it changes instantly.
The tight little figure eight balloons into these massive, sweeping, self-intersecting arcs.
Because you've changed the lever arms. By extending the coupler and the rocker, you're giving the mechanism a massive reach.
Right.
The short crank is still dictating that aggressive looping behavior. It's still pulling the system through a full 360-degree input cycle, but that motion is being amplified over a much longer physical distance.
So it's like...
It's like moving your wrist a tiny bit while holding a very long fishing pole. The tip of the pole swings through a massive arc.
That makes sense. The geometry amplifies the input. So let's turn the page in the atlas to the link A equals 2.0 series.
Okay, stepping it up.
We are lengthening the crank. We are giving the motor a bigger lever to pull with.
If we connect this to the bigger picture of mechanical design, this is where symmetry starts to break down in incredibly useful ways.
Useful how?
Well, if we set A to 2.0 with B at 3.5 and C at 3.5, the traces still form figure eights, but they are suddenly asymmetrical.
Yeah, looking at it, one loop of the 8 becomes this huge, wide, sweeping oval, while the other side pinches down into a much tighter turn. It looks really lopsided.
That lopsidedness is purely a result of the changing mechanical advantage throughout the full rotation of the crank.
Okay, break that down for me.
So at one point in the rotation, the bars align in a way that maximizes the push on the coupler, creating that wide sweep. But then, 180 degrees later, the bars are basically folded back on themselves.
Ah, so they lose their leverage.
Exactly. The mechanical advantage is terrible, and the coupler is pulled through a tight, slow curve.
And if we push the rocker out even further, keeping A at 2.0 and B at 3.5, but making C 4.0, we see something in the source material that I know is critical for manufacturing. We start to see sharp cusps.
Yes, a cusp. It's a point where the traced path doesn't just curve, right? It comes to a distinct mathematical point, and the line reverses back on itself.
I have to challenge this physically.
Okay, shoot.
A sharp point implies an instantaneous direction change. But in a physical piece of steel, moving at high speed, you can't have infinite acceleration.
No, you definitely can't.
So what is physically happening to the mechanism at a cusp? Doesn't the machine just rip itself apart?
That is an excellent pushback. And you are hitting on the exact difference between kinematics, the pure geometry of motion and dynamics, the actual physical forces of mass and acceleration.
Right, theory versus reality.
Exactly. At a cusp in a coupler curve, the velocity of that specific point on the coupler drops to absolute zero for an infinitely small fraction of a second.
It's stuck.
It physically comes to a dead stop and then accelerates in the opposite direction.
So it's basically a controlled collision with its own momentum.
Precisely. The mechanical shock, the jerk, which is the derivative of acceleration, can be massive. If you run a linkage with a cusp at 10,000 RPM, yes, it will tear itself apart from the fatigue of constantly stopping and snapping back.
So why use them?
Because if you are designing a low-speed mechanism, say a machine that punches a hole in a sheet of cardboard or drops a precise dab of hot glue onto a moving package, a cusp is your best friend.
Oh, because it stops.
Right. It gives you a built-in momentary stationary point to do your physical work, entirely dictated by the continuous rotation of the motor.
If you don't need a brake, the geometry acts as the brake. That is incredible.
That is very elegant.
Okay, let's keep lengthening the crank. We move to the link A equals 2.5 series, and here the visual language of the atlas shifts completely.
It really does.
At A equals 2.5, B equals 1.5, and C equals 2.5, the figure eights just vanish. The curves form these tight, overlapping sickle shapes.
Right. They look like the curved blade of a scythe. And the physics here have flipped. Notice that the crank, which is 2.5, is now significantly longer than the coupler, which is only 1.5.
The input lever is literally bigger than the bar it's pushing.
Exactly. So the crank is yanking this incredibly short coupler through very extreme
So
angles.
it's getting whipped around.
The short coupler doesn't have the length to absorb the arc of the crank, so it is forced to whip violently around its pivot point on the rocker. It creates this very aggressive, one-sided sweeping motion.
And if you adjust it slightly, keeping A at 2.5, but making B 2.5 and C 3.5, that sickle shape opens up into a distinct crescent.
Yeah, a wider crescent.
But looking closely at the source, inside that crescent, there is an internal looping structure. It looks like a crescent moon that tied itself in a knot.
That internal knot is a visual representation of mechanical conflict. The mechanism is reaching the absolute physical limit of its swing.
It's maxing out.
Yeah, it's pushing out as far as the bars will allow, crossing back over its own path as the rocker swings back, and then returning to the main crescent sweep. It is a highly localized, complex little dance happening right in the middle of a larger stroke.
Here's where it gets really interesting, though. When we hit the link A equals 3.0 series, the shapes in the atlas become incredibly extreme.
Very extreme.
At A equals 3.0, B equals 3.5, and C equals 4.5, they don't even look like loops anymore. They look like stretched needles.
The motion there is almost entirely linear for a long, long stretch.
It's basically a straight line.
Almost, yeah. The point on the coupler plunges forward in a near-perfect straight line, reaches the end of its stroke, does a microscopic hyper-fast turnaround at the tip of the needle, and shoots straight back.
And if you tweak that to A equals 3.0, B equals 4.0, and C equals 5.0, the paths plunge into deep overlapping curves with incredibly sharp pivot points at the very bottom.
Right.
It looks exactly like the flight path of a bird dive bombing into the water and swooping back up.
And think about where that dive bombing path is useful in industry. Imagine a high-speed bottling plant, right? You have bottles zooming by on a conveyor belt.
Okay, picturing it.
You need a mechanical arm to sweep down from above, firmly press a cap onto the bottle while moving horizontally with the bottle for a split second, and then violently pull back up and out of the way before the next bottle hits it.
Wow. That plunging sweep with the sharp pivot point is the exact mathematical curve you need to execute that. You just match the conveyor belt speed to the horizontal velocity of the mechanism at the bottom of the sweep.
Exactly. The geometry solves a complex 3D timing problem effortlessly.
Which brings us to the absolute extremes in the source atlas. The link A equals 3.5. When the lengths hit their upper limits, for example, if A is 3.5, B is 3.5, and C is a massive 6.5, the traces become almost entirely linear.
Right?
They look like long, flat straightaways with tiny, pinched loops at the extreme ends.
Getting a true, perfect straight line out of a rotating system of pinned linkages is actually one of the holy grails of classical mechanical engineering.
Really? Why is it so hard? Just use a sliding rail, right?
Because sliding rails involve friction, wear, and tolerance stack up.
Ah, maintenance issues.
Massive issues. If you have a linear bearing sliding on a rail in a dirty, dusty factory, it will eventually bind up, score the rail, and just fail. But a pinned linkage, it just has rotating bearings at the joints.
It may last longer.
Oh yeah, rotating bearings can be sealed, lubricated, and they last for decades.
Ah, I see. So if you can use swinging arcs to fake a perfectly straight line, you get the reliability of rotating joints, but with the output of a linear slider.
Exactly. These highly elongated coupler curves with the pinched ends are called approximate straight-line linkages. Engineers use them to drive pistons, guide cutting blades, and move heavy loads linearly without ever relying on a delicate sliding track.
And finally, looking at the very end of the series, when A is 4.0, B is 4.0, and C is 6.0, the traces stop looking like machine parts and start looking like astronomy.
You really do.
They form these massive, sweeping, nested orbits.
They look exactly like planetary paths or like the elliptical trajectories of comets orbiting a star.
Why does it look like that? Is there a shared mathematical reality between gravity and pinned bars?
In a way, yes. Both are governed by conservative forces and geometric constraints.
Okay.
In the linkage, the mechanism sweeps far out into the distance in a wide, slow arc, much like a comet at the apogee of its orbit, moving slowly because it's far from the sun.
Oh, wow.
Then as the crank pulls the mechanism back in tightly around the ground pivots, the mechanical advantage shifts, and the coupler whips around the focal point incredibly fast.
Just like a comet accelerating at perigee.
Exactly. It is a stunning visualization of how kinematic constraints map onto orbital mechanics all through pure geometry.
So if I'm that engineer in the 1960s, or even today designing a reliable, non-hackable physical system, I am just flipping through this atlas, basically shopping for a trajectory.
You are doing that same sweeping diving motion with digital sensors, multiple independent servo motors, and software requires incredibly complex programming.
And a lot of parts that can break.
Right. It requires timing belts that can stretch, encoders that can fail, and failure point management for power surges. But with this atlas, you find the shape, you cut 3 pieces of steel to the listed lengths, you pin them together, attach one dumb motor, and the motion is guaranteed.
It just works.
The code is physically baked into the steel. You literally cannot hack a steel bar.
That is just so satisfying. The physics does the math for you.
It really does.
But as brilliant as the 4-bar linkage is, it has a massive limitation. And this brings us to the paradigm shift in our source material today.
Right, because linkages can't do everything.
Because what if you flip through the entire atlas, all the thousands of shapes, and the exact motion you need just isn't there?
Right.
What if I need the machine to just stop? I mean, a swinging bar can't just freeze midair. If the motor is turning, the bars are swinging.
Exactly. This is the wall every mechanical engineer eventually hits with linkages. Linkages are bound by continuous algebraic functions.
So they never rest.
They cannot easily achieve true dwell, a period of absolute zero output motion while the input keeps moving. When you need motion that is totally arbitrary, highly customized, with weird pauses and sudden non-mathematical jumps, you have to leave the world of linkages.
And go
You
where?
have to enter the world of cams.
According to the source material, a cam is a mechanical member specifically used to impart a desired motion to a follower by direct contact.
That phrase right there, direct contact, is the entire paradigm shift.
Let's explore that. In a linkage, the motion is indirect. It's derived from the lengths of the bars pulling on each other. But in a cam system, you have 2 primary parts. The cam itself, which is the shape, and the follower, which is the part getting pushed.
Right.
The follower literally rests against the cam.
Yes. As the cam moves, whether it's rotating in a circle or sliding back and forth, its physical surface profile physically pushes the follower out of the way.
So it's just bumping into it.
Basically.
Yeah.
And the follower can rotate, reciprocate, or oscillate in response to whatever arbitrary shape is sliding past it.
So instead of relying on the indirect tug-of-war of swinging bars, you physically carve the exact motion you want into a block of metal, and the follower just traces that carving like a needle on a record player.
You've got it. If we connect this to the bigger picture, cams are the ultimate programmable mechanical memory.
Programmable memory.
Yeah. If you need a machine to move exactly 2 inches upward, stop dead for exactly 3 seconds, move another inch, and then instantly snap back to the start, you can't build a linkage to do that.
Too complicated.
But with a cam, you just take a piece of steel, cut a shape that pushes the follower up 2 inches, leave the surface perfectly flat for a distance that corresponds to 3 seconds of motor rotation, bump the surface up another inch, and then cut a sheer cliff face back to the baseline.
Wow. The physical shape of the cam is the program.
Exactly. The geometry dictates the code.
That is such a powerful conceptual framework. So let's look at the syntax of that code. Our source material details 7 distinct topologies of cams, showing how physical geometry dictates the behavior of the follower.
Let's get into it.
Let's start with the most basic foundational shape: wedge and flat cams.
These are conceptually the most straightforward. You have a wedge, literally just a ramp, and it interacts with a follower.
The sources outline 3 distinct configurations for the wedge cam. Let's break them down physically. Configuration A, the wedge translates, meaning the ramp itself moves in a straight horizontal line, back and forth, sliding on the floor. The follower is resting on top of the sloped surface. As the wedge pushes forward, the slope forces the follower to translate vertically, moving straight up and down.
It is the simplest conversion of motion. Horizontal straight line in, vertical straight line out.
Then we have configuration B. The wedge still translates horizontally, but this time, the follower isn't in a vertical track.
It's pinned.
Yeah, the follower is pinned at a pivot point off to the side, like a lever. So as the translating wedge pushes up against the underside of it, the follower is forced to oscillate.
It swings.
It swings back and forth on its pivot, like a drawbridge being pushed up by a boat.
Still a very simple transfer of force, but now we're converting linear motion into angular oscillating motion.
And finally, configuration C, which flips the script entirely. The wedge is completely stationary. It is bolted down.
Okay, so the wedge doesn't move.
Right. Instead, a guide mechanism forces the relative motion of the follower across the cam. So the entire carriage holding the follower moves horizontally across the stationary wedge, forcing the follower to ride up and down the slope.
In all three of these configurations, the core operating principle is identical. The specific slope, the physical angle of that flat or wedge surface, strictly defines both the rate and the total extent of the follower's motion.
Okay, but a flat wedge isn't very useful if you have a motor spinning continuously, right?
No, you'd run out of ramp pretty quick.
Exactly. Which brings us to type number 2, radial or disc cams. The sources note this is the most classic shape. When most of our listeners hear the word cam, this is absolutely what they picture.
Yes, think of the camshaft inside a traditional internal combustion engine. The cam is fundamentally a disc rotating on a central axis. The follower, which in an engine is connected to the valve, rests on the outer edge, the periphery of that disc.
But the disc is not perfectly circular. It looks like a lopsided teardrop, or like an egg spinning on a shaft.
Precisely. Because it isn't circular, the follower is forced to move radially. Radially means it moves outward directly away from the center of rotation and then back inward, following the uneven contour of the egg shape.
Following the bump.
Yeah, as the bulging, lopsided part comes around, it physically forces the follower up. As the circular baseline comes back around, a heavy spring slams the follower back down.
So rotary motion in, linear pumping motion out. Got it. Now for type number 3, swirl cams. This one is entirely different. It is a face cam.
A face cam.
So instead of the follower riding on the outside edge of an egg, the follower rides on the flat face of a spinning circular plate. And cut deep into that flat face is a groove in the form of a spiral.
Right. The follower has a small pin, or like a tiny steel roller, that sits trapped inside that spiral groove.
Trapped inside it.
Yeah. As the flat plate spins, the spiral physically pulls the follower either inward toward the dead center of the plate or pushes it outward toward the outer rim.
But here is a crucial mechanical rule highlighted in the source material regarding spiral cams that gave me pause.
Okay.
It says, and I'm quoting here, "The velocity of the follower is directly proportional to the radial distance of the groove from the axis of the cam."
It is a fundamental law of rotary dynamics.
Wait, let me push back on that because I want to make sure I grasp the physics here.
Go for it.
If the groove forces the follower to move faster simply because it is further out near the edge of the plate, doesn't that create a massive spike in kinetic energy?
Absolutely.
If I'm designing this, wouldn't the follower just snap under the G-force if it's forced to accelerate that fast at the outer edge?
That is an incredibly perceptive pushback, and it is exactly why cam design isn't just drawing pretty shapes. It is hardcore dynamic engineering.
So the math gets real.
Very real.
Mhm.
Let's look at the physics. Let's imagine the cam plate is spinning at a constant speed, say 1 revolution per second. Close to the center axis, the circumference of the groove is very tight.
Right.
In 1 second, only a few inches of groove drag pass beneath the follower.
So the follower moves slowly.
Right. But way out at the extreme edge of the disc, the circumference is massive. In that same exact 1 second, several feet of groove track are rushing past the follower.
Because it's covering more distance in the same time.
Exactly. Because significantly more physical distance is passing under the follower, for every degree the cam rotates at that larger radius, the follower is physically forced to move at a much higher velocity to keep up with the changing slope of the track.
It's like being on a playground merry-go-round, you know? The kid standing in the center is barely moving, but the kid hanging off the outside edge is experiencing massive centripetal force and velocity.
Exactly. That's it exactly. And to answer your pushback about the G-forces snapping the follower, yes, absolutely. If a designer doesn't account for the massive spike in kinetic energy and acceleration at the outer edge of a spiral cam, the mechanism will destroy itself.
The pin will just snap.
The follower pin will shear right off, or the groove will just gall and tear the metal apart. Engineers have to carefully design the curve of the spiral so that the acceleration profile remains within the material limits of the steel.
Right.
You can't just draw an arbitrary spiral. You have to calculate the dynamic forces at every millimeter.
That is wild. The math dictates the survival of the metal.
It really does.
Okay, let's move to type number 4. Cylindrical cams. Imagine a thick soup can rotating on its long axis. That is our cylinder. And there is a circumferential contour cut right into its surface.
The sources identify 2 very distinct follower behaviors you can extract from a cylindrical cam. The first is where a physical groove is milled entirely into the curved surface of the cylinder, wrapping around it like a wavy, drunken screw thread.
A drunken thread, I like that.
The follower sits trapped in that groove. As the cylinder rotates, the wavy groove forces the follower to swing back and forth in a constrained, oscillating motion.
Like the level wind mechanism on a fishing reel, where the little guide moves back and forth to lay the line evenly across the foul.
Perfect analogy. And the second type of cylindrical cam is where the end of the cylinder itself is contoured, rather than having a groove milled into the side. Imagine taking a pipe and cutting the end off at a weird, wavy angle.
Like a
Yes, exactly like a wavy crown. In this case, a spring-loaded follower presses against the contoured lip of that crown. As the cylinder rotates, the high and low points of the wavy lip push the follower, causing it to slide back and forth perfectly parallel to the axis of the rotating cylinder.
The source calls that a barrel cam. It seems like a fantastic way to turn rotary motion into parallel linear motion in a very tight, compact space.
It is incredibly space efficient, which is why it is used heavily in automatic machinery and historically in things like the mechanisms of early machine guns.
Now, type number 5, conjugate cams. The name sounds intense. The source describes it as a double disc setup. You have two distinct lopsided cam discs keyed together on the exact same spinning shaft, so they rotate in perfect unison.
Right.
But the follower isn't just a simple rod. It has a yoke shape, like a tuning fork, with two separate rollers on it. One roller rides on the first disc, and the second roller rides on the second disc.
What's fascinating here is understanding why an engineer would go through all the expense and trouble to manufacture the double disc setup.
Yeah, why do it?
We'll think back to the basic radial disc cam, the egg shape we talked about earlier. In a normal setup, you rely entirely on gravity, or a very heavy, stiff spring, to keep the follower pushed down tight against the cam surface as it rotates.
Right. The cam pushes it up, the spring forces it back down.
But what happens if you spin that cam at 12,000 RPM? The cam profile drops away. It goes from the high lobe back to the baseline, faster than the spring can physically expand to push the follower down.
I see. So the follower launches off the cam into thin air.
Exactly. It's called valve float in high-performance racing engines.
Valve float.
Yeah. The follower catches air, just like a roller coaster cresting a steep hill too fast. If the track drops away faster than gravity pulls the roller coaster cart down, you launch out of your seat. In a machine, losing contact with the cam means you have completely lost control of the physical timing.
And that's bad.
Very bad. Because when the spring finally catches up and slams the follower back down against the metal cam, the impact forces can shatter the mechanism.
And this is where the conjugate cam shines. Because it has two discs and two rollers acting on opposite sides of the yoke, the follower is physically locked in.
Exactly.
It's like having wheels on the bottom of the roller coaster track as well as the top.
That is the exact perfect analogy.
Ugh.
The conjugate cam physically traps the follower. One disc is mathematically cut to push the follower out, while the second disc is cut to the exact inverse profile to physically pull the follower back in.
Wow.
They are mechanically constrained in both directions simultaneously.
There's no spring to rely on.
No springs, no gravity, just pure force geometry. The source notes this is utilized for highly constrained, ultra-precise control. Use conjugate cams in high-speed, high-precision manufacturing environments where you absolutely cannot afford the follower bouncing, floating, or losing contact for even a microsecond.
That is brilliant engineering. Okay, moving to type 6, globoidal cams. The geometry here starts getting truly 3D.
Yeah, it gets weird.
The source describes them as having convex or concave surfaces. Imagine a football, or like the pinched shape of an hourglass, spinning on its long axis. That is your convex or concave globoid.
Right.
And just like the cylindrical cam, a wavy circumferential groove is cut into that curved 3D surface to impart an oscillating motion to the follower.
The reason you use a globoidal cam is to manage the three-dimensional pressure angles. If you have a follower that needs to swing in a wide, sweeping arc, a flat cylindrical cam will cause the follower to bind up at the edges of the swing because the angle of contact becomes too severe.
The pin will just jam in the groove.
Exactly. It'll just stick. But by making the cam concave like an hourglass, the surface of the cam actually curves to follow the arc of the swinging follower.
Oh, that's clever.
Yeah. The follower can swing through a massive angle while staying perfectly perpendicular to the cam surface at all times. It is all about managing the 3D geometry to keep the physical forces smooth, reduce friction, and keep the mechanism incredibly compact.
And finally, type 7, spherical cams. As the name suggests, this is a literal sphere, a metal ball rotating on an axis. The contour groove is cut directly into the surface of the sphere, and it transmits motion to a follower, forcing that follower to oscillate. but the source explicitly notes a very specific geometric constraint here.
Which is?
The follower oscillates about an axis that is exactly perpendicular to the axis of rotation of the cam itself.
Right. It transfers motion around a corner. If the spherical cam is rotating on a horizontal axis, the geometry of the sphere dictates that the follower is swinging on a vertical axis.
Ah, so it changes direction.
It is a highly specialized, very elegant way to transmit complex, contour, nonlinear motion around a strict 90-degree corner inside a tight machine housing.
Okay, so we've covered the 7 shapes, which I love calling the sheet music of the machine. Now we need to look closely at the instrument playing the tune.
The follower.
Right. We need to shift focus to the follower and how it choreographs that motion based on the physical coordinate systems detailed in the source material.
According to the text, followers are classified in 3 distinct ways. First, by their shape. Are they a sharp knife edge point, a flat mushroom face, or a rolling wheel?
Right.
That changes how they interact with the cam's surface friction. Second, they are classified by their movement. And third, by their alignment, specifically whether they are a radial follower or an offset follower.
Radial meaning the follower's axis points straight like an arrow through the dead center of the cam's rotation.
Yes, exactly. And an offset follower's axis is shifted slightly to the side of the center. Shifting it to the side radically changes the pressure angles. It allows the cam to push the follower up with a much gentler, smoother force.
But there's a trade-off.
Always. Though it sacrifices how quickly it can return on the back half of the stroke.
But I want to zero in on how the sources categorize their specific movement sequences, because this is where the programmable aspect really shines.
Yeah, this is key.
The material highlights 2 main kinetic sequences. First is RRRR, which stands for rise, return, rise. The source defines this as a continuous motion where the follower alternately rises and returns with absolutely no dwelling or pausing.
It goes up, it immediately comes down, it goes right back up.
Just constant movement.
It is continuous, relentless action. Think of the piston in your car engine. It never stops moving while the engine is running. Rise, return, rise, return.
So then there is the second sequence, DRRD, dwell, rise, return, dwell. In this sequence, the cam features specific dwelling sections followed by rising and returning. So what does this all mean mechanically? Why is a dwell so important?
The dwell is perhaps the most magical, vital thing a cam can achieve that a linkage cannot. A dwell is a period where the input motor is still spinning, the cam is still rotating, energy is still flowing constantly into the system, but the output follower remains completely, utterly stationary.
It doesn't move a fraction of a millimeter.
Nothing. It just sits there, frozen in time, waiting.
Oh.
Exactly. And doing this is geometrically impossible in a basic 4-bar linkage. In a linkage, if the input crank moves even 1 degree, the geometry shifts, and the coupler and rocker must move.
Right, because they're all tied together.
There's no way to just tell a swinging bar to stop while the rest of the mechanism keeps moving. But in a cam system, it was effortlessly easy. To create a dwell, the engineer simply makes a section of the cam's profile perfectly circular, maintaining a constant radius from the center of rotation.
Because if the radius doesn't change, the follower has no slope to ride up or down.
Right. As that perfectly round, constant radius section slides underneath the follower, the distance from the center doesn't change, so the follower isn't lifted or dropped. It dwells.
So imagine you have a complex machine assembling a delicate microchip. It needs a robotic arm to drop down, that's the rise. It needs to stay perfectly, rigidly still for exactly 1.5 seconds, while a laser welds a tiny gold contact, that's the dwell.
Perfect example.
And then it needs to immediately retract out of the way, that's the return. And you control that 1.5 seconds of absolute stillness entirely by calculating how many degrees of the cam circle you leave perfectly round based on the RPM of the motor.
You are physically carving time into the geometry of the metal. It is beautiful.
It really is.
But it also introduces a massive analytical and manufacturing challenge. When you get into designing these complex 3-dimensional dwell motions, especially with cylindrical, globoidal, or spherical cams, you can't just draw them on a flat piece of graph paper like you can with a simple flat disk cam.
Which brings us to a fascinating analytical note from the source material regarding coordinate systems. To properly analyze and work with these complex 3-dimensional cam motions, the text explicitly states, a second approach is to work with cylindrical coordinates.
This raises an important question. How do modern engineers mathematically model these physical, swirling 3D parts to make sure they work before they commit to cutting expensive steel?
I know our listeners who deal with CAD and 3D modeling deal with Cartesian coordinate mapping all the time, your standard X, Y, and Z grids.
Right, the usual boxes.
But if you try to use Cartesian math to map the wavy, wrapping groove of a cylindrical cam, it is a nightmare. The friction of converting Cartesian splines into toolpaths for a modern 5-axis CNC mill is massive. The trigonometry is deeply complicated because the surface is constantly curving away from the X and Y planes.
Exactly. If you use Cartesian coordinates, you are fighting the geometry of the cylinder. But if you switch your mathematical approach to cylindrical coordinates, everything aligns perfectly with the physical reality of the part.
As a refresher, cylindrical coordinates don't use XYZ boxes. They define a point in 3D space using a radius how far out from the center axis, an angle how far around the circle it has rotated, and a height how far up or down the cylinder.
But utilizing the cylindrical mathematical system, engineers can map the exact surface of a cylindrical or spiral cam effortlessly. The angle variable directly represents the physical rotation of the cam over time, and the height variable directly represents the linear motion of the follower.
So you can literally write a relatively simple mathematical function for the CNC machine that says, as the angle goes from 0 to 90 degrees, smoothly transition the height from 0 to 2 inches and keep the radius constant.
Yes, that pure math is then fed into the CNC software, generating the G-code, which drives the cutting tool perfectly along the surface of the steel. It ensures the physical groove exactly matches the theoretical kinetic profile.
It's all connected.
It is the mathematical bridge between the theoretical code of motion and the physical steel that executes it on the factory floor.
It is incredible to think about the layer upon layer of physical and mathematical problem solving required just to make a machine move exactly how we want it to.
And that brings me to a final provocative thought I want to leave our listeners with today. As we move deeper into an era of robotics and automation that relies almost entirely on digital servos, electronic linear actuators, and millions of lines of software code, we tend to view mechanical linkages and cams as quaint or old-fashioned.
Yeah, a lot of people think of them as antiques.
But remember this. These purely physical mechanical geometries cannot be hacked.
A software glitch or a corrupted update cannot make a 4-bar linkage suddenly trace the wrong curve.
Exactly. An electromagnetic pulse or a power surge cannot make a hardened steel cam forget its precise dwell time. They offer a perfect, unalterable physical truth of motion that electronics still struggle to replicate with the same raw, unbreakable reliability.
They don't fail like a computer.
They don't require reboots, they don't get malware, and they don't lose their memory when the power goes out.
The geometry is the truth. That is a brilliant point. So next time you see a machine moving in a complex, repetitive, beautiful way, whether it's an ancient weaving loom, the camshaft in your car engine, or an automated high-speed packaging line, ask yourself, is there a digital brain behind that movement, or just a brilliantly designed piece of rotating steel?
It's definitely something to think about.
Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.